because constant acceleration motion problems are common, which they're useful, they keep coming back all throughout physics, and they're the first sort of problems that require a little bit more insight than what we've been doing so far. It's worth doing a little bit on just walking through a few problems together. So this is basically about solving a couple of problems together and talking about the problem-solving method, as well as getting the particular answers to come out. As usual with classes, it's not so much the answer you get that matters, it's that you're able to show a consistent, reasonable reasoning process. So that's what we'll do today. This is basically the universal mathematical physics problem-solving recipe. 1. Read the problem. You would be shocked how much easier it is to correctly answer a problem when you've actually read it through. And I don't mean run your eyeballs over the text, I mean wrestle with it and pull out the things that are important and understand and conceptualize the problem. 2. Draw a picture and pull appropriate values in the problem. This sounds almost cartoonish, almost kindergartenish, but it's actually really important. People are generally visually oriented thinkers. We use a vast amount of our brain to process visual images. The visual cortex consumes something like 20% of the energy in general for a human brain. It's like having an extra processor. It's like having a graphical processor unit attached to your brain. You might as well use it. And by sitting down and having to draw the picture, it requires you to wrestle with what's going on and pull out the things that are important and what's fluff and can be left behind. So it sounds goofy, but it's generally, in almost all cases, until you get really fluent with this, it's almost always a good idea to just take 30 seconds and draw a picture. 3. Write down any universal equations that apply. For us, this will probably be a constant acceleration equation, which holds in any case where there's, well, constant acceleration. So these are always basically true. Translate your picture into particular values for those universal equations. You'll hear me often say, particularize your solution. Take the thing that's always true and put in the things you know are true in this case. Actually, almost all mathematical problem solving comes down to having a universal and a particular and then putting them together to see something new. 5. Identify your desired quantities. 6. Solve for the desired quantities. That's me putting all that math that you know and sweeping it under the rug. It's kind of obnoxious to say, just solve for it. But I mean, literally, take your problem. You've now put everything down, figure out what you want, and rearrange the equations until you get what you want equals all the other stuff. And then 7, and this cannot be emphasized enough, so I'll highlight it several times. Highlight, right? So read the problem again. Once you think you're done, go back and scan the problem to make sure that you have answered what it actually asked for. One of the common tragedies in introductory physics is a student who takes a problem that's complex, breaks it down into simple steps, follows all the simple steps through, and is so proud that they've got an answer, they forget to notice that they haven't finished the problem, that they got the really hard part done, but now you need to double the time to get the time of flight or something silly like that. And then they lose credit, and on the AP possibly even lose the passing score, because they just didn't check that they were answering what they were asked for. In the end, it's a problem-solving science, and until you actually solve the problem, you're not done. So you should go back and scan it. This is a less intense scan. This is just reread the problem to make sure you haven't left anything out, as opposed to step 1 where it was like really delve in. But definitely take the time to do that. Sample problem 1. Step 1. Read the problem. So let's read the problem. Horatio is riding a go-kart that has an acceleration of 2.4 meters per second squared. He is traveling at 7.6 meters per second when he spots Imogen ahead of him. She is moving at 12.4 meters per second in the same direction. How long will it take Horatio to match her speed? All right, that's our reading our problem. Now let's go through and pick out the stuff that's important and get rid of the stuff that is not. Well, we definitely are going to want to use the acceleration. That's going to be important for us. We're going to want the initial speed that he has, and we're going to want the final speed that he has, which is hers. All right. What kinds of things do you not really need to worry about? What kinds of things can we skip? It doesn't really matter that it's a go-kart. It hardly matters that it's Imogen as long as we have that bit. So there's a lot of stuff in there that isn't very important. Step 2, draw the picture, pull appropriate values from above. So the picture is, at least at the moment, we have here is, I don't know, go-kart with Horatio. And then sometime later we have the go-kart with Horatio. And what do we know? Well, we want to go, we know that at the start he's moving at 7.6 meters per second. And at the end, since he's traveling in the same direction as she and at the same speed, he ends with a velocity of 12.4 meters per second. What else do we know? Well, we know that there's an acceleration, which was given as 2.4 in the direction, right? He needs to speed up, so he accelerates in the same direction, and we get something like that. And then what we don't know, we can say our initial time is 0. We always have that freedom, but we want to know what is the final time. So that's the thing. Notice what's not on our picture in any way is either the initial or final positions, because nothing in this question asked us about it. So when we pull them out, they don't go on our diagram. They don't show up. All right. Step 3, write down universal equations that apply. So we'll need some blank paper. And we'll say, well, we're talking about velocities and times, and we have an acceleration. So our universal equation is going to be something like Vfx is Vix plus the acceleration in the x direction times delta t. That's our universal equation. For a thing undergoing constant acceleration, this equation is always true. It's not really this problem, it's everything. All right, we've taken our picture. We've done number 4, translate the picture into particular values. So what are we looking for? Well, we are looking for, ultimately, is delta t. Right? That's the thing we're seeking. What things do we know? Well, we know the acceleration that was given. We know the initial velocity that was given. We know the final velocity. So we look here and we say, oh, we're actually in pretty good shape. You could really just put values in right away. So we have, if I remember correctly, we have 12.4 meters per second over here. We have 7.6 meters per second here. And we have 2.4 meters per second squared here. And we're still, of course, looking for delta t. Then we just do algebra. And in general, I will not do algebra for you because algebra fluency is a requirement for this class. But as a reminder, after maybe a long time since you've done a lot of problem solving, we would, for instance, here we need to isolate delta t. So the very first thing, we want to get it by itself in a term. So we need to get rid of everything that isn't a term involving delta t. So I'll subtract 7.6 from both sides. That gives us that we have now 4.8 meters per second is 2.4 meters per second squared times delta t, a suspiciously convenient number. When we do the division, now we divide both sides by the thing in front of delta t, so as to isolate the delta t. And over on the right, of course, we have that this, anything over itself is 1, and I no longer need to write it, so I have just delta t. You might have math teachers who tell you you canceled it, and that's fine. All right, I'm not opposed to that terminology, but what you're really saying is anything over itself is invisible. And of course, 4.8 over 2.4 is 2, so we get 2. And meters per second over meters per second squared, well, meters per second, we divide by flipping and multiplying, and then again we see that we have this is 1, and all but one of those is 1, so we're left with 2 seconds equals delta t. A lot of people get freaked out by reading it that way. Delta t, the time we wanted, was 2 seconds. We just flip it by reflexive property. You can solve this any way you want to solve it, and as I said, in general, I'm not going to tell you how to solve things algebraically because you know how to solve things. Step 7 is read the problem again and make sure we've actually answered what was required. I'm not going to flip back to the other screen, but I will reread it. Horatio is riding a go-kart which has an acceleration which is given. He's traveling at some speed when he spots Imogen moving at some other speed in the same direction. How long will it take Horatio to match her speed? And we have found that time, so we are done. This is a place where it's just been typed up really fast because my handwriting is pretty terrible, but there you go. All right, sample problem 1b. Horatio is riding a go-kart at an acceleration of 2.4 meters per second squared. He's traveling at 7.6 meters per second when he spots Imogen ahead of him, moving at 12.4 meters per second in the same direction. How far in meters does Horatio travel before he matches her speed? So notice that this is almost the same problem. In fact, of course, it was just cut and paste. But instead of asking how long, which is a thing that implies time, now we're asking how far, a thing that implies distance. So we're looking for answers of delta x. Let's go back to our set process. We've read the problem. Let's draw a picture. Well, it's going to be the same picture, but I'm going to redraw it anyway. So moving along, here is Horatio and his go-kart. And then sometime later, here he is again. And what do we know? Well, we know that he is moving forward originally at 7.6 and eventually at 12.4 because he's accelerating at 2.4 meters per second squared. But now what we want is we want this delta x, right? So we'll start off by saying x initial we can always set to 0. So now we're really looking for what is Horatio's final position. Notice that we know something that we didn't, that the problem here doesn't tell us explicitly. It's the same problem, so we know that the time is going to be the 2.4. It's going to be the 2 seconds that we found, but we're not going to use that. Right? We can, and I think at the end I'll go back and do it. What if we use that information? Instead, here we're going to move forward as if this had been a problem all by itself. All right, we want to write down our equation that applies and do the rest of the problem. How do we know what equation applies? Well, we can go through and say, well, what things do we know and what things do we not know? And what jumps out is, as written in O1b, we don't have the time and we aren't asked the time. So the equation we have that doesn't have the time but doesn't ask for the time is that the final velocity squared is the initial velocity squared plus 2 times the acceleration times delta x. And since we were looking for delta x, that's good, especially because we have the acceleration and we have the 2 velocities. So again, we're basically there in one step, and we can just start putting stuff in. So now we're going to translate the picture into these particular values, which means we end up at 12.4 meters per second. Remember, we're going to square it. And we started at 7.6 meters per second, and again, we're going to square it at some point. And now we have twice the acceleration, which was given as 2.4 meters per second squared, times the thing we're looking for, which is delta x. And then we can grind out these numbers. I'm actually going to solve it over first for delta x. This is alternate. If you're like, I know how to solve that, just solve it. But in general, for me, I like to rearrange things first before I plug into calculators. So I'm going to bring, I'm going to subtract off this, which leaves me with, oops, that I'll have 12.4 meters per second quantity squared minus 7.6 meters per second quantity squared. That will equal 2 times 2.4, I'll do this as 4.8 meters per second squared delta x. So delta x is that thing, 12.4 meters per second quantity squared minus 7.6 meters per second quantity squared, all over 4.8 meters per second square. And now I can just throw it into a calculator, and I'll get 20. And then we have meters squared per second squared over meters per second square, so we flip and multiply. The second squares cancel, one of the meters cancels, and we end up with 20 meters, which is the right unit, so yay, that worked fine. All right, and that's sort of the quick and dirty way to do it, that if we had just hit that problem clean, we might have done it that way.